All right, I have an interesting question to solve today about anagrams. So the full extent of the question right off the bat here is, determine if a pair of numbers are anagramically divisible irrespective of argument ordering. What? That makes no sense. In fact, the professors provided 2 full pages of explanation just so we can understand exactly what that means. It took me almost 2 hours of staring at the explanation, searching the internet, and copying code from Stack Overflow just to understand everything. And I'll try to compress those 2 pages into a single sentence here to try and better sum it all together. Given the binary representation of 2 integer numbers as separate strings, find the quantity of pairs of substrings within each string which are anagrams of each other, and process if those quantities are evenly divisible with each other. Alright, that's admittedly even worse than before, but it allows us to break it down so that we can create a program out of it. So let's tear apart that sentence. First, we need to discuss what anagrams are. If you've ever played the game Wordscapes on your phone or the board game Bananagrams, you might have an idea what it is. Basically, it's 2 words or sets of letters that have the same letters within them. So for instance, kitchen and thicken are anagrams of each other because they use the same letters just in a different order. Once you understand this, you can start to break down the question. So the first part of the question asks for the binary representation of 2 integers. So this means we need 2 integers as input, and a function int to binary that returns a string variable of 0s and 1. The second part of the question uses our knowledge of anagrams and is a reference to an exercise made by HackerRank called Sherlock and Anagrams. The simplest way I can think to explain it is if you were given a word, such as kitchen, or any set of random letters really, you can cut the word into every single combination of substrings, including just single letters. So let's actually just use a simpler example here, such as MOM. So every single combination of substrings, including single letters, would be M, O, M, also MO, and OM. Now the full set does technically also count, but we won't have a match with it because there's only ever one instance of all the letters. So this doesn't matter about ordering, right? This is just about substrings. So how many of these substrings, how many substrings are there? We've got 1, 2, 3, 4, 5. How many of them have pairs, sets of 2 with each other? So in this case, we've got M is a pair with M, and MO is a pair with OM because they use the same letters O and M. So whereas O itself does not have any substring pairs, all right? So the answer to this is 2 pairs. You've got 1 pair here and 1 pair here. That's a big pen, but it gets you the idea, right? So the answer, if we were provided with MOM, is 2. Great. For more complicated ones, there's other examples given, such as, let's see here, ABBA is another one here. So if we break it down, ABBA, and we split it down to every single set of substrings, which the single substrings first would be A, B, B, A, then of 2 would be AB, BB, BA, and of length 3 we have ABB and BBA. So that's every single combination there. All right, because we're only going forward because ordering doesn't matter. So how many of them have pairs? Well, here's a pair here. Here's a pair here. Here's a pair with these 2. And here's a pair with these 2. So we've got 1, 2, 3, 4. So the answer for this would be 4 pairs. Hopefully that makes sense. Now, this is obviously the most complicated part of the assignment, so if we don't fully understand it yet, that's okay. We're going to use some test-driven development to help us as we explore this problem. For now, just know that it's a function which takes a string and returns an integer. Finally, the last part of the question just asks us to take the output of the function Sherlock and anagrams for each string and compare if they are evenly divisible with each other. This can be split into a couple functions. One called isAnagramDivisible, which takes two integers and returns true or false, and the other function is a simple isDivisible function, which returns whether two integers are divisible with each other, irrespective of the ordering of those two integers. So let's write this out. The first function we need is int to binary. The next function we need is Sherlock and anagrams, which takes a string and returns an integer. Okay, the other one we need is anagram divisible, which takes two integers and returns true or false. We also need a simple function isDivisible, which takes two integers and returns true or false. All right, so now that we understand the basic outline of the program, we can actually start writing it so we can get the shell together and use some test-driven development to help us along the way. So let's get coding. So for this code, I'm just going to use Notepad, and we'll start off by creating a simple header file. I'm going to go ahead and use C++ for the development of this code here. Okay, so this first one here, we just need to include first IOStream. And now we'll just do some other stuff. So we'll define the functions that we already talked about. So that kind of gives us the rough structure. Now, in the header file as well, this is where we can use test-driven development. So I started using Catch2, which was a great thing that Carl introduced me to, and I found a great way to make it work for this program. So Catch2 has its own main function that it likes to use. So the easiest way I found to set it up is to surround our main function basically in a preprocessor if-else, and then Catch2's main function in another preprocessor if-else, so that only one main function can run at a time. Either our program will compile as a test case, or it will compile as the actual program itself. So to surround it in that preprocessor directive, what we do is we say define testing, and we'll say it's false for right now. And what we'll say is if testing equals true, then we will define catch config main and include the catch one header file, which is awesome, and end that if statement. So we'll just make a little note here in code. Pretty good. And I'll just, for the sake of making it very obvious what it is you need to change, we'll do that right there. All right, so now we've got our header file ready and some test-driven development that we can implement. So let's go ahead and create a new file. So to start off with the C++ file, we will of course include the header file. And since we're dealing with strings a bunch, I don't want to have to type out std for the whole program. All right, so this is the first part here. These are our testing cases. So it's only going to execute this next part of the code if the testing constant in the header is set to true. And now we can define our test cases now. So this is great. That means we can test the actual program out first while we've only got a shell in place. And once we start developing our Sherlock and anagrams function, we've got some tests implemented that will test it out right away for us. So our first test case is going to be anagram divisibility. And that uses the function is anagram divisible. So for this first part, we're testing out is anagram divisible. So that's kind of the main function that we're dealing with. And we're going to require is anagram divisible 5, 8. So in the example that's provided to us here, we're given the numbers 5 and 8, and we are told that they are anagramically divisible because 5, which is turned into 101, and 8, which is turned into 1000, have a total of 2 and 4 substrings that have pairs. So they are anagramically divisible. So if we go back to our main function, so 5 and 8, if they're sent through that function that we will determine, they must return true. Okay, that's a basic one there. We're also going to do a test case of 2 and 1 because that tests out an extreme value where if the function is given something where it's only given a 0 in it, in this case 2, right, which is a 1 and a 0, it has 0 anagramically divisible pairs, which means in our isDivisible function, it's going to be passed as 0, which could result in a divide by 0 error if we're not careful. So it's good to have these extreme test cases on either side of extreme values and lower values, so we're able to make sure that that works as well. So if we go through here, we'll make another test case. And we're going to require basically all the examples that it gives us here. ABBA is 4, ABCD is 0. And because it provides all of these examples for us, it makes really great test cases to verify that we're doing things properly in our function. All right, and we're also going to test some extreme cases as well. All right, great. So we've got that test case out of the way. We just got a couple more to run through for the other functions that we're going to make. Wonderful. Okay, so now we will just say surround that in an else. So we've got the testing, and now we've got the else, and we're going to say this is our main. So basically by surrounding it in an else, we're going to say, so your main program compiles on its own, the testing program compiles separately. It just means in your main.cpp file, you can't have any functions you would want to test out. So you've got to keep it a little separate. So this just makes it easier for our simple testing case. Keeps it simple. All right. All right, so let's create our main function. Now I like to do this because we're going to be compiling in our Ubuntu subsystem, and I like to add a little bit of color to it. So we'll add some weird characters and you'll see it looks kind of cool after. So now we need to ask for the variables. Now, all we really need to do at this point is, are they divisible? And then at the end of the main function, turn 0. Wonderful. So now we just need to write out some shells of our functions. Great. So we've got the basic outline of our program. So if we compile it, so if we go to our header, make sure our testing is false, and if we run Ubuntu, we need to move the catch2 header file in here. So, and g++ main.cpp. Oh, great. And if we run it, welcome to binary anagrams. Perfect, we've got that. Please enter the first number, 5, 6. Are they divisible? Yes. So it appears it works even though our actual program does literally nothing. So this is where test-driven development comes in. So if we go back to our header file here and we change testing to true, save it and recompile. Oh, that's not gonna work. Takes a couple minutes to compile just because catch2 is quite a big header file. All right, and now let's run it. And we'll see that our test cases, 2 passed and 2 failed, 4 passed, 2 failed, just because we're returning true for a couple of functions means that some of the tests work, but your program is not working properly if anything fails. So Sherlock and Anagrams mom equals 2, it returns 0 instead of 2, require into binary is 101, obviously we're getting nothing there. So great, now we know that our program is not working, and we can go and start writing it properly. So let's go back and change testing. Well, actually, we can just keep it true. But let's go back here and let's start writing in our functions. So we've got the basic shell of our program, which is great now, and we've got all of our tests developed. So now we just need to actually make these work. So to start with, let's write out some documentation so we know what it is exactly we are trying to get these functions to do. So to start with, is anagram divisible? Let's write some documentation. So I'm going to use Doxygen and create some documentation. So the first one is anagram divisible. Okay, a little complicated, but that is what it is. And we've got parameter. First int is the first integer to compare, and at param int second to compare, and return values. Great. Now let's add that to another function here. Great. Just a couple more here. Great. So we've got our documentation done. We've got the basic outline of our program. Now we just need to figure out the actual math itself. So let's start with the easy stuff. So is anagram divisible? What we need to run is really simple. Return is divisible. Actually, just to kind of split this up a little bit, we'll say second int string, because we have to pass strings into Sherlock and anagrams, equals int to binary. Okay, that just makes it a little easier to return the values. So Sherlock and anagrams First int string, second int string. That's it. That's not too complicated there. So that one is done. And the next one is divisible. We just need to, so remember that first test case we had on the extreme side here. So is divisible 0, 0 needs to be true. So first off, we just need to say if first int is 0 or else return first int modular second int 0 or great. So is divisible is good. All right, and then this one convert into a string of binary digits. So we'll keep the return nothing at the end in case we don't have anything else to return if it provides an invalid argument. So we're going to actually make this a quick recursive function. So we'll just start with an int and so let's run through this code really quickly here. So you're given a num, let's say for instance, you're given the number 2, right? Which is greater than 0. And we come in here and we say num modular 2 is 0. So a is 0. And then we're going to run int to binary num divided by 2. So we're going to assume that int to binary works properly. So num divided by 2, 2 divided by 2 is 1. So currently string is equal to 1. And then we're going to append a, which is 0, and we're left with 1, 0, which is perfect. That's what we want. So these are extreme values, and this is if we get nothing. So there we go. So all of our functions work now, except for Sherlock and anagrams, so the main part of our function. So let's actually test it out. So our testing is still set to true, and if we recompile it again, we will find that all of the other tests that previously failed, such as int binary, should now work. And the only ones that are going to fail is anagram computations. So we'll run it again. And that's what we found. Anagram computations and, oh, integer to binary. So we ended up with the 0, 1. So this is great. This tells me that I had something go wrong here. And what exactly is it? Oh, because, you know what, we can't have that. Because this one will eventually pass 0. I just want to test out now another extreme value. So we want to do integer to binary conversions. And we're just going to do a new one. Require int to binary 0 equals 0. Just make sure that works. And I think the recursion will actually make it work just fine, but we'll try it again here. So recompile that and run it again. And we've got, interesting. Hooray! So the only problems we have now are anagram computations. So we know for sure that the other tests have passed properly. That's great. So we know we've got this one figured out now. So it's just a couple special cases. If it's 1, return 1. If it's anything higher than that, do that. And if it's 0, return 0. Great. Now, obviously this program isn't complete yet, and you might be thinking to yourself, Andrew, you didn't follow the instructions. You're supposed to map everything out before you start programming. But I thought this was a cool opportunity to showcase some test-driven development as proven by my int to binary function, so that we can see how a program can develop, even if you have no idea how the mathematics behind it work. If you know what your inputs and outputs are supposed to be, and you can map out some test-driven development, it'll help guide you in how to create the function itself. So let's continue on and see if we can't get this program to work fully. So let's go back to our drawing board. So we need to remember what we are trying to produce from this function. So we're doing Sherlock and anagrams. So let's just move this down a little bit here. So we're given a string and we're trying to return an integer. All right. So we need to determine the amount of matching anagrams within a string. Could be any letter. It could also be any number, really. We're really just dealing with zeros and ones, but we also want letters to work in our case as well, so we can test it out properly. Now at this point, you have to fight the urge to Stack Overflow the answer and paste it into your code, because that doesn't let us learn anything. But of course, studying code is actually a good way to figure something out, and that is how I figured this out, was looking it up online to fully understand it, because honestly, I couldn't get it on my own. So I wasn't sure at first how to even brute force the algorithm, but if we step it through, we can kind of figure it out after staring at it for a little bit. So let's break it down. So you need to iterate through each and every combination of letters. This means, for the example mom, we must iterate through M, O, M, MO, and OM. Then we find that M and M are a pair, and MO and OM are also pairs. So since their ordering doesn't matter, these two count as pairs. So we're just looking for matching letters. So my first thought was some sort of extremely complicated iteration for C strings, going through everything and comparing them with different orders. So we would break it up into every single iteration. So we'd have basically an iterator for each and every set of strings. And then once we've got this huge store of all strings, all combinations, basically a hash map, we would then have to compare them in every single ordering. So if you were given basically a string of length k, 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 as that's the provided example, you'd have to have the string k, 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 so the 4 separate ones, then the strings k, 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 and k, k, and the strings k, 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 and k, k, k. And then we need to rearrange the ordering. So we'd have to compare, this is 1 and that's 2. And of course this is 1 and that's 2 and that's 1 and that's 2. And then we would need to compare 2 and 1 for KK, this one here, with this one, both as 1, 2, and as 2, 1 as well. Just an absolute mess of, this is probably a bad example, that's a lot of Ks, but the idea is you'd have to iterate through every single permutation, which would just, as far as time complexity goes, you'd have big O of n for iterating through each and every one of those, n being the length of the string. So by the time you've iterated through and logged everything, you've got O squared, or n times n, and then you would also have to rearrange everything. So you'd times it by n squared, and then times it by n again to iterate through and then compare all your substrings. So you'd end up with big O n to the 5, basically 1, 2, 3, 4, 5, which is just bad. We don't want to do that. But how do we do it? Well, the other way you can look at it is if we look at the fact that ordering doesn't matter, MO and OM. So what if every single letter had some unique value that whenever they were added together or multiplied together, their products, created another unique value that, when combined, produced the same. So if you combine an M, which has a unique value, and an O, it doesn't matter what order, so long as when they're combined together, they produce the same value. Well, how do you do something like that? You can use these wonderful things called prime numbers. Hooray! How do we use prime numbers, though? Well, if we map every single letter to a prime number, actually what we'll do is we'll start at 2, 3, z equals 5, D equals 7, dot, 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 26 letters, plus 0 and 1, we get all the way to 1 equals 103, and 2, or sorry, and 0 we'll say is 107. Okay? So every single character is mapped to a prime number. So then, if you multiply the prime numbers together, so for instance, in our case, M, which is the prime number 41, and our other one, O, which in this case is 47, if we multiply, so we've got MO and OM, so M is 41 times 47, and we get, I should know this, but I don't, so I will calculate it. It was 1,927. And if we do it the other way, of course, 47 times 41, we also get 1,927. And no other combination of prime numbers, when you multiply them together, will give you 1,927. That's fantastic. So we now have a system where any combination of letters will give us a unique value. So that helps us with the fact that they don't have to be ordered. So that's wonderful. Now, how do we apply this in code? So the first thing we're going to want to do is let's go back to our header here, and we're going to add one more function method here. We're going to do void, and this is just going to be a function that will help us create all these prime mappings that we need to do. We also need to include. Okay, hooray, that's great. So now let's go back here, and we're just going to add some globals. So now we can go back into our code in this function and basically start writing. So we need a few variables to start. Int n, long key, result. We also need characters here so that we can go through them. And we need an unordered map for this function as well to iterate through. Okay, you know what, let's actually do this primes one as well. So we've got our primes here. Great. So to start off this function, result, we'll start with 0. So we're already at n squared here, but we kind of have to go through every iteration. And then we need to go third one. Okay, now it's hard to explain this. So basically what it's saying is, in our example, kitchens, the first for loop says for every letter, so all 8 letters. Then the next one says for every remaining letter. So what it does is it takes the remaining amount of letters. So when the first for loop's on K, this one iterates through all 7 of the remaining ones. But then when the first loop is then on I, it will iterate through the remaining 6 letters after that. So with that though, we're only going to get combinations of 2 letters each. So in order to get the rest of them, we have to say for every combination, I guess. So that way on the first loop, the first one's on K, this one will be on I. Looks like my pen is out of digital ink. And then the third loop will basically iterate through, you get your T, your C, H, E, N, S, and then when it goes through the next set for these two, it will then go and be at I, and then T, and then the C, H, E, N, S, onwards and so forth. So obviously though, with your 3 for loops, it is going to give you a big O, my pen has stopped working, of n cubed. There we go. So let's get back to our code. So basically what we're doing is going through, so let's take this again. Let's say we've got M, O, M. Okay. So we go through the key of M, which was 47 and 41 and 47. So we're multiplying. So we've got, in these maps, we've got the first permutation, which is just M. So we get 47, 41, 47. Then we also get these added, multiplied together, which was 1927. Okay, and we also get OM, which is 1927. And then we also get all three of them multiplied together, which is some big number, 90,569. But yeah, so basically what it's doing is it's computing all of these and storing them in a hash map labeled. So the key, it's the next value. So we're left with this map, right? Where you've got a bunch of keys. So we've got a map here and map 1, right? Which is this first combination equals 47. Okay, and we've got our map 2 equals 41. Okay, and then map 3 equals 47, right? And we keep iterating through. So map 4 equals 1927, okay? And it goes dot, 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 basically. So now we've got this nice, basically all this does is it creates a nice data set for us that we can go through and look for comparisons, look for matching numbers. Great, so now we're gonna go through all these values and look for pairs. Okay, I think that should work. Now we need to return result. Okay, so that's that. Now, one more thing here. We've got this init primes that we need to document. Okay, so I think we're good here. So, try to wrap this up. Let's compile it. So we're still in testing mode, which is fantastic. We can just stay there. Let's compile it again. See if I missed anything. And run it. All tests passed. Hooray! So that means it works. So now let's actually run the program. False. Save that. Then go back here. Recompile it again. Compiles much quicker. Run the program. Welcome to binary anagrams. Please input the first integer. So just to test out here, we had our test cases at the beginning. Let's check them out. So the one given in the instructions was 5 and 8 needs to be true. 5 and 8. Are they divisible? Yes! Hooray! Look at that, we did it. So the last thing we need to do here is let's compile our documentation. So we've created all these Doxygen parameters. So let's go ahead and run doxywizard. Now the reason this takes a while actually is that it is compiling the documentation for catch 2 as well, which is a little more than we need for our program, but it's kind of cool that it will capture everything that's in all of the different header files. So that's great. Doxygen is finished, and we'll just go show HTML output. There we go, binary anagrams documentation. So if we go to our main.cpp, and we can see test cases, is divisible, is anagram divisible, Sherlock and anagrams, and we've got determine the number of pairs of substrings, parameters s, the string to compare, integer, all our wonderful things that we wrote down are all there for us into binary. There you go. So that's it. That's the end of assignment 2. Thank you for watching and have a great day.